Hello everyone, welcome to our weekly revision program. In our today's discussion, we will focus on work, energy, and power. Stay with us. Work is force times distance, but only the force component in the direction of motion counts. If you apply a force in the direction of the displacement, then to calculate the amount of work done on that object, you can simply multiply the force with distance. And force in direction of motion is what matters. For instance, if a force makes some angle theta with horizontal, and assuming that the block is moving along the horizontal direction, which is to the right direction, to calculate the amount of work done on this object, you can find the cosine component of the force and multiply with the parallel displacement. Therefore, the scientific definition of work done is defined as the scalar product of force and displacement over which it acts, and we can simply calculate work done by using dot product of force and displacement. Previously, you have learned about dot product of two vectors. So whenever you multiply two vectors using a dot, then the product will be scalar, meaning that scalar physical quantity has no direction, and hence work done is a scalar physical quantity. And from the definition of dot product of two vectors, F dot with S, it is equal to magnitude of the force times magnitude of the displacement times cosine of theta, where theta is the smaller angle between the two vectors. And the unit of work is Newton meter, and its SI unit is Joule. Let's look at this diagram on the screen. So we have four different blocks and we are applying the force in different directions. If you look at the first one, the vertical component of the force does not cause the block to move to the right. The energy imparted to the box is evident by its motion to the right. Therefore, only the horizontal component of the force actually creates energy or work. If you see the second one, when the force and displacement are in the same direction, you get a positive work done, and the angle between the force and the displacement is 0 in this particular example, meaning cosine of 0 is 1 and you will have a maximum positive work done. For the third block, when the force and displacement are in opposite direction yet still on the same axis, you get a negative work value, and this negative doesn't mean the direction. It simply means that there is a loss of energy, and the angle between the force and the displacement is 180 degrees, and because of this we will have a negative energy, and therefore we will have a negative work done. And for the last one, the force and the displacement are perpendicular, and therefore you get no work because the angle between the force and the displacement is 90 degrees, meaning cosine of 90 is 0, and therefore there is no work done. Now we define that if the force and the displacement are parallel to each other, you can simply multiply the magnitude of the force with the magnitude of the displacement to calculate work done. Let's look at this one. We have a block and we need to displace this block from the ground to a certain height change in y above the level ground. So the minimum force required to displace this block in the upward direction is equal to the weight of the object. So by applying this force, which is equal to mg in the upward direction, if we displace this block vertically upward, then the force and the displacement are in the same direction, and the amount of work done is the same as F times change in y, where F is the same as mg and change in y is h. So we can calculate work done by using an equation W equals mgh, and this is the work done by the person lifting the box in the upward direction. When we look at the reverse one, if we want to lower this block towards the ground, still we are applying a force in upward direction, which is the same as the weight of the object, but we are displacing it in the downward direction, meaning the force and displacement are opposite, and because of this, lowering the box will give us a negative work done, and it is equal to minus mgh. Now if we see work done by gravity, the direction of gravitational force is in the downward direction, and if the block is moving again towards the ground, since both force and displacement are in the same direction, then the work done by force of gravity will be positive. Let's look at work done by constant force and work done by a variable force. So when we talk about work done by constant force, since we have a constant force, by applying this force, so when we look at work done by a constant force, the force is constant means when you draw force versus position or force versus displacement graph, you will have a constant, or you will have a horizontal straight line parallel to the position line. And to find the amount of work done by this constant force to displace a certain object from position x1 to position x2, you can simply draw an area and calculate the area enclosed by the graph. And here in this case, since the force is constant, you always have a rectangle, and the area enclosed by the graph is equal to the amount of work done by that constant force. But if you see work done by a variable force, for instance, let's take a spring force or elastic force, it is a linearly varying force, meaning, as you can see on the screen, force versus displacement or force versus distance graph is an inclined straight line. So there is an increase in position, or there is an increase in distance as we increase the amount of force on that spring or on that elastic material, and this will happen in a linearly manner. And to calculate the amount of work done and to calculate how much work is done to move this block attached with a certain elastic material, it is equal to the area enclosed by the graph. And in this case, and you will have a right angle triangle, and vertically it is denoted by the force, which is the same as kx, and horizontally it is denoted by x, which is the stretch of the elastic material. Therefore, half times base times height is equal to half times f times x, but f is kx. And finally, you'll have work done to move a mass on a spring to a certain distance x is equal to half kx squared, where k is the spring constant. But if it is not linearly varying force, in this case you have to apply the concept of calculus and find the amount of work done just simply by calculating the area under a force versus distance curve. The other point is about conservative forces and non-conservative forces. So a force is said to be conservative if the work it does on an object moving between 2 points is the same, no matter the path the object takes between the points. Whereas a non-conservative force is generally dissipative. This release usually becomes heat or sound. Work done against a non-conservative force cannot easily be recovered. So when you say conservative forces, these are just forces that do both positive and negative work done, and in a closed loop these positive and negative work done are equal and opposite. When we sum up, total work done will be zero, meaning these conservative forces do not do some amount of work done in a given closed loop. And we can take gravity, elastic force and electrical force as an example of these conservative forces. When we see dissipative forces, these forces do only just negative work done. So in any closed loop, they do some amount of negative work done. And these forces are like friction and viscosity. And they do negative work done means there is a loss of energy, and it will be changed into like heat and sound energy. Now, when you look at energy, as you all know, energy is defined as the ability or the capacity to do work. And energy makes change, and energy moves cars along the road and boats over the water. It bakes a cake in the oven and keeps ice frozen in the freezer. It plays our favorite songs on the radio and lights our homes. Energy makes our bodies grow and allows our minds to think. And people have learned how to change energy from one form to another so that we can do more easily and live more comfortably. And there are different types of energies. And for the time being, let's look at components of mechanical energy. The first one is kinetic energy. So when we say kinetic energy, it is the energy possessed by an object because it is in motion. And this kinetic energy is calculated by half mv squared, where m is the mass of the moving object and v is the speed of that object. And the other type of energy is gravitational potential energy. And this energy is possessed by an object because of a gravitational interaction or because of its position above the level ground. And this gravitational potential energy is calculated by mgh, where m is the mass of the object, g is acceleration due to gravity, and h is the height above the level ground. The third type of energy is elastic potential energy. This is energy stored in an elastic material, and it is calculated by half kx squared, where k is the spring constant or elastic force constant, which is measured in Newton per meter, and x is the stretch of the material or the compression of the material, which is measured in meter. Now, so far you have learned about kinematics and Newton's laws in our previous discussions. Now let's see what happens when we apply both to our new formula for work done. So let's assume that we are applying a certain constant force on a block, and that block is displacing with a displacement x in the direction of the force. Now, to calculate the work done, since the force and the displacement are parallel, work W equals F times x. But from Newton's second law of motion, this force equals mass times acceleration, assuming that there is no frictional force. And instead of F, if we substitute m times a, then work done equals max. And since we assume that the force is constant, the acceleration is also constant, and therefore the motion is uniformly accelerated motion. And for a uniformly accelerated motion, you can use an equation called v final squared equals v initial squared plus 2ax. And from this, let's make ax to be the subject of the formula, so that ax equals v final squared minus v initial squared divided by 2. Now we already have w equals max, and instead of ax, if you substitute v final squared minus v initial squared over 2 and distribute m, finally you will have w equals half mv final squared minus half mv initial squared. But half mv final squared is the final kinetic energy, and half mv initial squared is the initial kinetic energy. And when you deduct the initial kinetic energy from the final one, then you will get the change in kinetic energy. And so what we really have is called the work energy theorem. And it's basically means that if we impart work to an object, it will undergo a change in speed, and thus a change in kinetic energy. Since both work and kinetic energy are expressed in joules, they are equivalent terms. And this work energy theorem states that the net work done on an object is equal to the change in kinetic energy of the object. Let's say lifting mass at a constant speed. Suppose you lift a mass upward at a constant speed, change in V equals 0, and change in kinetic energy is 0. So what does the work equal now? So since you are lifting at a constant speed, your applied force equals the weight of the object you are lifting. And since you are lifting, you are raising the object a certain vertical displacement h or y. And to calculate the work done equals F times x, and the minimum force required to displace this object in the vertical direction is equal to the weight of the object, which is mg, and x is the vertical displacement, it is the same as h. And finally, to calculate the work done to displace an object in the upper direction will be equal to mgh. But this mgh is the same as potential energy. So when you lift an object above the ground, it's said to have potential energy. So we can apply work energy theorem just by considering all the forces that the object may come across. So work done by friction or work done by dissipative force is always negative, and it's equal to the change in kinetic energy and potential energy. And these two energies are equal and opposite. When you look at conservation of mechanical energy, first let's define what mechanical energy is. So mechanical energy is the sum of kinetic energy and potential energy. And the law of conservation of energy states that energy can neither be created nor destroyed, but it only transformed from one form to another form. If you look at conservation of mechanical energy in particular, since the sum of this kinetic and potential energy at initial point is always equal to the sum of kinetic energy and potential energy at the final point. If you look at the law of conservation of mechanical energy, then the sum of kinetic and potential energy at initial point is always equal to the sum of kinetic energy and potential energy at the final point, assuming that there is no energy loss by friction, air resistance, or other external factors. If you see conservation of energy in spring on the screen, then at position 1 we have a kinetic energy of 2 joule and a potential energy of 0. So the sum of this kinetic and potential is 2 joule. But after a while, when it reaches to a certain vertical displacement, which is in compression, it reaches to maximum compression, means at that instant, so there is no kinetic energy, meaning all the kinetic energy is converted into potential energy. And after a while, when it's just stretched to the maximum point, then again the kinetic energy will be 0, and at that instant it also changed into potential energy. And in the meantime, when it comes to equilibrium position again, it will have a maximum speed, meaning there is no potential energy and all the mechanical energy is stored in terms of kinetic energy. So when you look at the simulation on the screen, there is a simple pendulum moving here and there, and the bob is displacing, and to reach to the equilibrium position it will have a maximum speed, and in that case it will have also a maximum kinetic energy. That particular position, the potential energy will be 0. But when it reaches to the highest point on the right and left side, it will acquire the maximum potential energy, meaning at that instant there is no speed and there is no kinetic energy. So the mechanical energy is expressed in terms of potential energy. So for an object which is moving in a certain elevation, it will acquire both gravitational potential energy and kinetic energy. So the sum of this potential energy and kinetic energy should be constant. And in that case, we can say that energy is conserved. If you look at conservation of energy springs and gravity, assuming that there is an elastic material moving with a certain elevation, then we have to consider gravitational potential energy, spring potential energy or elastic potential energy, and kinetic energy. So the sum of these three energies should be constant at any position in order to say that energy is conserved. The last point for our today's discussion is power. So one useful application of energy is to determine the rate at which we store or we use it. We call this application power. So power is defined as a time rate of doing work, which is work done divided by time, but work done is the same as force times displacement divided by time. So displacement over time is speed or average speed or velocity. So average power is calculated by the dot product of force and average velocity. And to find the instantaneous power, you can calculate it by just force times instantaneous velocity. In addition to this, we can also define power as the time rate of transferring of energy. So it might be the time rate of transferring of potential energy, or it might be the time rate of transferring of kinetic energy. So we can calculate power by using mgh over t or half mv squared over t. And the SI unit of power is watt. So 1 watt is equal to 1 joule per second or 1 Newton meter per second. Now let us see some practical examples on the topics that we have discussed so far. When we see the first one, it says that a 70 kilogram base runner begins to slide into second base when moving at a speed of 4 meters per second. The coefficient of kinetic friction between his clothes and the earth is 0.70. He slides so that his speed is 0 just as he reaches the base. So the first question is, how much energy is lost due to friction acting on the runner? And the second one is, how far does he slide? So to calculate the amount of energy lost due to friction, we can apply work energy theorem. So work done by friction is the same as the change in kinetic energy. So since he finally stops and his speed is 0, there is no final kinetic energy, but initially he was just moving with a speed of 4 meters per second, and we know the mass of this runner. So work done by friction is equal to change in kinetic energy. So it is the same as final kinetic energy minus initial kinetic energy, but the final kinetic energy is 0. So we'll have work done by friction equals negative of half mv naught squared, where v naught is the initial speed. So the mass and the initial speed can be substituted, and finally work done by friction will be minus 560 joule. So the minus sign indicates that this work done is negative. And to calculate the distance that he slides, first let's find the frictional force. So as you all know, frictional force is equal to coefficient of friction times normal force. And in this case, the normal force is the same as the weight of the runner. So it is equal to mu mg. You can substitute mu, m and g, and finally force of friction becomes 480.2 Newton. Now work done by friction equals force of friction times displacement x times cosine of theta. But you have to bear in mind that the force of friction and the displacement are in opposite direction, and hence theta is 180 degrees. After this, you can substitute all the known variables, and finally the unknown one will be x, and you can calculate, and x becomes 1.17 meter. The second example said that a 5-gram bullet moving at 600 meters per second penetrates a tree trunk to a depth of 4 centimeters. The first question is, use the work energy theorem to determine the average frictional force that stops the bullet. And second one is, assuming that the frictional force is constant, determine how much time elapses between the moment the bullet enters the tree and the moment it stops moving. So to calculate the average frictional force that stops the bullet, again we have to apply work energy theorem. So work done equals the change in kinetic energy, and final kinetic energy is 0 here because it stops finally, and work done by friction equals minus half mv0 squared, and all are given. You can substitute and you will have work done by friction equals minus 900 joule. But we are asked to calculate the frictional force, and to find this, work done by friction equals frictional force times displacement x times cosine of theta. But since it is frictional force, force and displacement are in opposite direction, and cosine of theta is -1. Now you can substitute all the known variables, and frictional force becomes 22,500 Newton. When you look at the second question, we are asked to calculate the time elapsed between the moment the bullet enters the tree and the moment it stops moving. So we know this frictional force, the only force acting on the bullet is this one, and it is the same as the net force and equal to mass times acceleration. So since you know the mass of the bullet, you can calculate the acceleration, and it will be the same as 4.5 times 10 to the power of 6 meter per second squared. After this, you can apply definition of acceleration, which is v final equals v initial plus at, and the final velocity is 0. The initial velocity is given, which is 600 meters per second, and you already know the value of a, so you can make t to be the subject, and finally you can calculate it, and it will be equal to 1.33 times 10 to the power of -4 second. A 2-meter pendulum is released from rest when the support string is at an angle of 25 degrees with the vertical. What is the speed of the bob at the bottom of the string? So as you can see on the screen, you have a bob at certain height h, but the length of the string is L, and to calculate this vertical position h, it will be the same as total length L times L cos theta. So to calculate h, or to find the height of the bob above the equilibrium position, h will be the same as the total length of the string L minus L cos theta. So theta is given, L is given. You can substitute and find h, and it will be equal to 0.187 meters. Now if you have this as a given, then so you can calculate the total energy stored in the bob, which is equal to mgh. Now we have to apply conservation of mechanical energy to calculate the speed of the bob at the bottom of the string. So we already know the value of h, we have the mass of this, and so to calculate the speed of the bob at the bottom of the string, first let's find the value of h, or the height of the bob above the equilibrium position. So to find h, this h equals total length of the string times, so to calculate h, where h is calculate the height of the bob above the equilibrium position, this h equals total length of the string L minus L cos theta. So theta is given and L is given. You can substitute and know the value of h, and it is equal to 0.187 meter. Now to find the speed of the bob at the bottom of the string, let's apply the law of conservation of mechanical energy. So at the highest point, the bob will have an energy in potential energy form, but when it reaches to the lowest point or the bottom point, that total gravitational potential energy will be converted into kinetic energy. Therefore, mgh is equal to half mv squared. When we say mgh naught, h naught is the height of the bow at the final height. So when we see mgh naught, h naught means the height above the equilibrium position, and when you say half mv squared, v stands for the speed of the bob at the lowest position. This will be the maximum speed, and h naught is the maximum height. Now if we equate mgh naught with half mv squared, then you can cancel out m by m, so gh naught will be the same as half v squared. Then we can rearrange and substitute the known values, and finally the speed of the bob at the bottom of the string becomes 1.94 meters per second. Let us see our final example for today's discussion. A slingshot consists of a light laser cap containing a stone that is pulled back against two rubber bands. It takes a force of 30 Newton to stretch the bands 1 centimeter. Question 1 says, what is the potential energy stored in the bands when a 50-gram stone is placed in the cap and pulled back 0.2 meter from the equilibrium position? And second question is, with what speed does it leave the slingshot? So to calculate the potential energy stored in the band, first you have to know the spring constant K. So from Hooke's law, we know that F equals K times X. The force is given, which is 30 Newton. X is the stretch of the material, which is 0.01 meter. Then if you calculate K, it becomes 3000 Newton per meter. Now you know the spring constant, it is the same in all cases. Then to calculate the potential energy stored in the bands when a 50-gram stone is placed in the cap and pulled back 0.2 meter from the equilibrium position, the energy stored becomes half kx squared, and it is the same as 0.5 times k, where k is 3000 Newton per meter and x is given, which is 0.2 meter. You can square it and you can substitute, and finally it will be 300 joule. And to find the speed that the stone leaves the slingshot, you have to apply the law of conservation of mechanical energy. All this stored energy, or all this stored elastic potential energy, will be converted into kinetic energy. So half kx squared, or this 300 joule, will be equal to half mv squared. And then you can crisscross and finally find the value of v, because all the other variables are known, and therefore v becomes 109.54 meters per second. I hope you enjoyed our lesson. That's all for today. Thank you.